Welcome to Fuzzy Mathematics, the Basics. At the beginning of this course, we have known that a fuzzy set is characterized by its membership function. The relations between and operations on fuzzy sets are defined pointwise in terms of degrees of membership. The properties of operations on fuzzy sets totally depend on the properties of operations on real numbers in the closed interval from 0 to 1. And then we talked about the algebraic structures with certain properties. But the discussion wasn't confined to the fuzzy power set or to the closed interval from 0 to 1, but more generally, posets. Now it's time to come back. Determine whether this algebraic structure is a Boolean algebra, a soft algebra, or an optimal soft algebra. We will answer these questions at the end of this lecture. Let's start with the very beginning. Let A and B be two fuzzy sets. A is a subset of B if and only if A of x is less than or equal to B of x for all x. It is easy to see that the inclusion relation on the fuzzy power set of x is a partial order. We will check the three properties of partial order quickly. First, reflexivity. Suppose A is a fuzzy set. A of x is less than or equal to A of x for all x. So, A is a subset of A. Next, antisymmetry. If A is a subset of B and B is a subset of A, that is, A of x is less than or equal to B of x. B of x is less than or equal to A of x. Then, A of x equals B of x for all x. Thus, A is the same as B. Next, transitivity. If A is a subset of B, B is a subset of C, then A of x is less than or equal to B of x, and B of x is less than or equal to C of x. So, A of x is less than or equal to C of x for all x. That is, A is a subset of C. The inclusion relation is reflexive, antisymmetric, and transitive. So, H is a partial order. The fuzzy power set, together with the partial order, the inclusion relation, is a poset. Next, is it a lattice? Determine whether each pair of fuzzy sets has both a supremum and an infimum. What are they if it has? First, let's look at the supremum. Suppose C is a fuzzy set such that C is the upper bound of A and B. That is, A is a subset of C, B is a subset of C. So, A of x is less than or equal to C of x. B of x is less than or equal to C of x for all x. Here, A of x, B of x, C of x are real numbers. So, C of x is an upper bound of A of x and B of x. By the definition of supremum, we have the maximum of A of x and B of x is less than or equal to C of x. Considering the definition of union of fuzzy sets, we have the union of A and B of x is the same as the maximum of A of x and B of x. So, the union of A and B of x is less than or equal to C of x for all x. That is, the union of A and B is a subset of C. On the other hand, it is easy to see that A is a subset of the union of A and B is a subset of the union of A and B. That is, the union of A and B is an upper bound of these two fuzzy sets. So it is the least upper bound of the two fuzzy sets. That is, the supremum of A and B exists, and it is the union of A and B. Similarly, we can prove that the infimum of A and B exists, and it is the intersection of A and B. So this poset is a lattice. This is the algebraic structure induced by the lattice, the fuzzy poset, together with the two binary operations, the union and the intersection, where the supremum of A and B is the union of A and B, and the infimum of A and B is the intersection of A and B. The relationship between the partial order and the two binary operations is as follows. A is a subset of B if and only if the union of A and B is B, if and only if the intersection of A and B is A. The algebraic structure is induced by this lattice, so it obeys the following laws: the idempotent laws, the commutative laws, the associative laws, and the absorption laws. Next, we are going to talk about the boundedness of the lattice. Does this lattice have a greatest element? Yes. The greatest element is the universal set. Does it have a least element? Yes. The least element is the empty set. Is it bounded? Yes, it's bounded. This is a bounded lattice. By the definition of the greatest element and the least element, we have the empty set is a subset of A, a subset of X, for all fuzzy sets in the fuzzy poset. By the relationship between the partial order and the two binary operations, we have the domination laws and identity laws hold. First, the domination laws. The union of A and the universal set is the universal set. The intersection of A and the empty set is the empty set. Next, the identity laws. The intersection of A and the universal set is A. The union of A and the empty set is A. Next, completeness. Is it a complete lattice? If any non-empty subset of the fuzzy poset has both a supremum and an infimum, then it is a complete lattice. Suppose I is an identifier set. Determine whether the supremum of AIs and the infimum of AIs exist. Suppose the supremum of AIs and infimum of AIs exist. What are they? Guess. The supremum is equal to the union of AIs. The infimum is equal to the intersection of AI. You can prove it yourself. And this is a complete lattice. Next, the distributive laws. If we take the union of A and intersection of the two fuzzy sets, we can distribute the union over the two fuzzy sets. If we take the intersection of A and the union of the two fuzzy sets, we can distribute the intersection over the two fuzzy sets. Of course, you could check the two identities directly. Here we will check the infinite distributive laws instead. If we can prove that it has infinite distributivity, then it has distributivity. Infinite distributive laws. Union distribute over intersection. Intersection distribute over union. We will prove the second equality by showing that the membership functions of the two fuzzy sets are equal. By the definition of intersection of fuzzy sets, the left-hand side is going to be the infimum of A of X and the union of AI of X. By the definition of union of fuzzy sets, the union of AI of X is the supremum of AI of X. By the infinite distributivity of real numbers in the closed interval from 0 to 1, H is going to be the supremum of the infimum of A of x and AI of x. Infimum distribute over supremum. By the definition of intersection of fuzzy sets, the infimum of A of x and AI of x is the intersection of A and AI of x. By the definition of union of fuzzy sets, it is going to be the union of the intersection of A and AI of x. Now we have shown that intersection distribute over union. Similarly, we can prove that union distribute over intersection. This completes the proof. Next, we will talk about the complementary laws. Suppose A is a fuzzy set. The complement of A is denoted by this notation, where the membership function is defined as follows. The complement of A of x is 1 minus A of x for all x. Determine whether the complementary laws hold in this algebraic structure. Do you remember the examples of young and old? In general, suppose A is a fuzzy set. If it is not a crisp set, then the union of A and the complement of A is not the universal set, and the intersection of A and the complement of A is not the empty set. This lattice is not complemented, but the double negation law and the De Morgan laws hold, so the algebraic structure is a dual lattice. Similar to the case of distributivity, we will check the infinite De Morgan laws instead. If we can prove the infinite De Morgan laws, then we have the De Morgan laws hold. The complement of the union equals the intersection of the complements. The complement of the intersection equals the union of the complements. We will prove the first equality by showing that the membership functions of the two fuzzy sets are equal. By the definition of complement of a fuzzy set, the complement of the union of x equals 1 minus the union of x. By the definition of union of fuzzy sets, the union of AI of x equals the supremum of AI of x. By the definition of complement of a real number in the closed interval from 0 to 1, 1 minus the supremum equals the complement of the supremum. By the infinite De Morgan law in the lattice of real numbers in the closed interval from 0 to 1, it is going to be the infimum of the complement of AI of x. By the definition of complement of real number, the complement of AI of x equals 1 minus AI of x. By the definition of complement of a fuzzy set, 1 minus AI of x equals the complement of AI of x. By the definition of intersection of fuzzy sets, the infimum of the complement of AI of x equals the intersection of the complement of AI of x. Therefore, we have shown that the complement of the union equals the intersection of the complements. Similarly, we can prove that the complement of the intersection equals the union of the complements. This completes the proof. Next, density in the fuzzy power set. The fuzzy power set is dense if, for every two fuzzy sets, A is a proper subset of B, then there exists C in the fuzzy power set such that A is a proper subset of C, a proper subset of B. Suppose A is a proper subset of B. That is, A of x is less than or equal to B of x for all x. And there exists x0 such that A of x0 is strictly less than B of x0. Define C of x is A of x plus B of x over 2 for all x. Then A of x is less than or equal to C of x. less than or equal to b of x, and a of x0 is less than c of x0, less than b of x0. So A is a proper subset of C, a proper subset of B. Is it dense? Yes, the lattice is dense. Now we can answer the questions we put forward at the beginning of this lecture. We know that a Boolean algebra must be complemented. However, the complementary laws do not hold in this algebraic structure, so it is not a Boolean algebra. Is it a soft algebra? A soft algebra is a dual lattice together with boundedness and distributivity. It is a dual lattice. It has boundedness and distributivity. So it is a soft algebra. Is H an optimal soft algebra? An optimal soft algebra is a dual lattice together with density and infinite distributivity. It is a dual lattice. It has density and infinite distributivity. So it is optimal soft algebra. The fuzzy power set, together with the two binary operations, the union and the intersection, and the unary operation, the complementation, is an optimal soft algebra. At the end of this lecture, we will list the 4 important algebraic structures in set theory or in fuzzy set theory. We have discussed the first 2 algebraic structures in detail. As to the latter 2, you are familiar with them, at least to some extent. The lectures on this topic will give you a new perspective on them. And do you remember these questions? Now you may solve all of these questions on your own. That's the end of this lecture and the end of this topic. Next time, we will move on to a new topic, fuzzy operators. Thank you.